Welcome to Lecture 6. Let me help you read the notes for this lecture. It says, so far all of our problems have been dealing with homogeneous regions. And what we mean there is that really, to be honest, all the problems that we've dealt with have been posed as though they were in free space, or and alternatively they could have been in a material, but the material is the same everywhere. So this is what we mean by homogeneous, is that in our problem domain the material that's present is the same everywhere throughout the region, or possibly there's not even any material present, and there's just vacuum everywhere. But now we want to begin to consider somewhat more realistic problems, and so it says here, but what do we do in the case of an inhomogeneous region? And keep in mind now, we're still assuming that the region is source free, but now the material properties are changing as a function of position in the region. So if you go back to answer what we would do in this case, let's go back to our earlier derivation. Remember that from Maxwell's equations we have that the divergence of D is equal to rho, where rho is the charge density and D is the electric displacement. Now again, we still have a charge-free region, so that means that rho is still 0 as it was before. So this equation becomes that the divergence of D is equal to 0. Now, as we mentioned before, D is equal to epsilon times E, where E is the electric field intensity and epsilon is the permittivity. But now, since epsilon is changing, since we're considering now that we may have an inhomogeneous region, that means that epsilon may have different values in different parts of the region. And since that's the case, we can't take it outside the divergence operator. If there's no time variation, it's still okay for us to define an electric potential V that is related to E in this way. E is equal to the negative of the gradient of V. And so we'll plug that in for E, and then of course we can pull the negative sign outside the divergence operator and then multiply E sign by a negative sign to get rid of that. And so this becomes the divergence of epsilon times the gradient of V is equal to 0. And keep in mind now that epsilon is a scalar, V is a scalar, but the gradient of V then is a vector. And so we have a scalar here times a vector, which of course will give us a vector field, and the divergence of that vector field is equal to 0. Now, if we go ahead, just as in elementary calculus we have rules for taking the derivative of a product, well, the same is true here in vector calculus for taking the divergence of a scalar times a vector. And what we'll get is the gradient of that scalar dotted with the vector, and then plus we get the scalar times the divergence of the vector. And the divergence of the gradient of V, that's del dot grad V, is equal to del squared V. So when we operate on this scalar times this vector with the divergence operator, this is what we'll get here on the left hand side, and this is equal to 0. And just note that trying to give you a slightly better view here. Okay, now that's better. Note that if epsilon is equal to constant, then this first term, the gradient of a constant, would be 0, so the first term would drop out, and this would be a constant, and we can multiply both sides by 1 over that constant, and then we just get del squared V equals 0, which is of course the equation that we had before. So this is, everything we have here is consistent with what we had before. Now, as before, we want to keep this simple and just look at a one-dimensional world in which the partial derivative with respect to y and partial derivative with respect to z are 0. So this means there's no variation at all in the y or z direction. And so then, if that's true, the gradient of epsilon just becomes d epsilon dx. The gradient of v is dv dx. And when we take the dot product of these, actually, let me back up. The gradient of epsilon actually is d epsilon dx times the unit vector in the x direction. And likewise, the gradient of v is dv dx times the unit vector in the x direction. And then when we take the dot product of those two vectors, when we dot those two unit vectors in the x direction together, we just get 1. And so we're left with 1 times d epsilon dx times dv dx. And of course, that's just d epsilon dx times dv dx. So that's a more careful way of explaining what's going on there. And then we just bring epsilon del squared v. If there's no variation in the y or z directions, then del squared v becomes d squared v dx squared. And so this is the equation that we will arrive at in a one-dimensional case. And once again, we point out that if epsilon is constant, as was the case in our first project, then d epsilon dx would be 0. This term would drop out, and we could multiply the remaining equation by 1 over epsilon to get d squared v dx squared is equal to 0, which is what we have here. Okay, and which is what we did before. So this is all familiar to you. It's just this is exactly what you had before, except now d squared v dx squared is getting multiplied by epsilon, and there's also this one additional term present. Now, how do we solve this problem numerically? Well, as is explained here, the numerical solution poses no real difficulty usually, and so let's explain why. Suppose that we wanted to enforce this equation at node I in our problem domain. Well then, if epsilon, now remember we're assuming that epsilon is a changing function, so let's give it a name f of x, and if epsilon is equal to f of x, then this equation right here would become d epsilon dx would become df dx at node I, where we're thinking now of how we would enforce this equation at node I. So d epsilon dx at node I would become df dx at node I, and then dv dx at node I, okay, we would have v of I plus 1 minus v of I minus 1 over 2 delta. This is our second order accurate finite difference formula for the first derivative. And then the second term here, epsilon is f of x, so this would be f of x evaluated at node I, and then d squared v dx squared, as usual, would become v at node I plus 1 plus v at node I minus 1 minus 2v of I over delta squared is equal to 0. So that would be your equation at node I, and you would repeat this for all of the interior nodes, and then at the nodes and the boundaries you put the boundary conditions and solve the problem just as before. So it's really straightforward. Now, what if we know epsilon at each node? What if somebody has given us epsilon at each node, but we don't actually have a formula for epsilon? So see, here we were assuming that epsilon is equal to some known function of x, which we called f of x. But instead, suppose that we just knew epsilon at the nodes, but we didn't have a formula. Well, this would still be straightforward. We would just take those values of epsilon in each node, and for df dx, we'd use the derivative formula, epsilon of x plus the finite difference formula for the derivative. We'd have epsilon at node I plus 1 minus epsilon at node I minus 1 over 2 delta, and then this remains the same, and f of x at node I would become epsilon I, the value of epsilon at node I, and then this second derivative of v comes down just the same, and we get 0. So all of that is pretty straightforward. But there is one case that poses a little bit more of a challenge. And so let's talk about that now, and then that will lead into our next computer project. A problem arises when epsilon has a sudden jump in the region because then d epsilon dx is not defined. You see, here in our equation, we have d epsilon dx times dv dx. But if epsilon is a discontinuous function of x, then that means that this derivative is not defined. And that can easily happen. If we have an abrupt change in epsilon, then that means epsilon is a discontinuous function of x, and so this derivative is not defined. So what do we do in that case? And in fact, that's a common case to encounter. So what can we do in that case? Well, we recall from electromagnetic theory that at any charge-free interface, in other words, by interface we mean where epsilon is taking that sudden jump from one value to another value. And charge-free means simply that there's no charge at that surface between those two regions. So at any charge-free interface, d normal must be continuous. Okay? So even though epsilon is discontinuous, it's changing abruptly, d normal, the normal derivative, the normal component of d, which in this case is the x component of d cannot take a jump. It has to be a continuous function. So in this one-dimensional case, we have dx is continuous across any interface. Okay? So let's assume that here's the problem we have in mind. We have like a domain x equals 0 here at the left-hand boundary, and x equals L over 2, L2, not L over 2, but L2. X is equal to L sub 2 at the right boundary, but here at some interior point, x equals L1, we have a break. And see, from x equals 0 to x equals L1, epsilon is constant and equal to the value epsilon 1. But from x equals L1 to x equals L2, epsilon is constant and equal to epsilon 2. And epsilon 2 here is different from epsilon 1. So that means that at x equals L1, that's where the interface is. And it's the interface between these two regions, and epsilon does take an abrupt jump, a sudden change in value there at that interface. So this is the kind of problem we want to solve. And remember, what we just said, that electromagnetic theory dictates that even though epsilon is changing abruptly at that point, dx cannot change abruptly at that point. So that means that dx evaluated at L1 minus, and what I mean by L1 minus is just a tiny distance to the left of L1. So it says dx evaluated at L1 minus is equal to dx evaluated at L1 plus. And as you might guess, L1 plus is just a very small distance to the right of L1. So it's saying dx here, just, a nanometer to the right of L1 is equal to dx just a nanometer to the left of L1. Even though epsilon is changing there abruptly, dx cannot change abruptly. So that is the key for solving this problem. Okay, and let's see how that will be used. So keeping in mind that d is equal to epsilon e, then dx becomes epsilon ex. Now just to the left of L1, that becomes epsilon 1 ex, because just to the left of L1, epsilon is equal to epsilon 1. But just to the right of L1, dx is epsilon 2 ex. So we have epsilon 1 ex evaluated here at x equals L1 minus is equal to epsilon 2 ex evaluated at x equals L1 plus. And remember now that E is equal to the derivative of V, the electric potential, negative derivative of V. So we're going to substitute minus dV dx for E sub x on both the right and the left. And we'll get, and then the two minus signs can be canceled. And so we have epsilon 1 times dv dx just to the left of L1 is equal to epsilon 2 times dv dx just to the right of L1. And now to evaluate these derivatives, we want to use the one-sided derivative formulas that we used before. You will recall that in a very early project we had a problem where we had a derivative boundary condition on the right-hand side of our boundary, and so we had to use a one-sided derivative formula to express that derivative boundary condition. Well, a similar kind of thing is happening here. When we calculate dv dx just to the left of L1, we only want to involve nodes that are to the left. So in other words, right here, this dv dx at L1 minus, we don't want to, for dv dx, we don't want to take the value at I plus 1 minus the value at I minus 1 divided by 2 delta, because we don't, for this derivative just to the left, we don't want to use any values from the right. And likewise for this derivative just to the right, we don't want to use any nodal values from the left. So we'll use for the derivative just to the left, we will use these three values. Now it's still going to be the derivative evaluated at this point at L1, but we're going to use the one-sided derivative formula that involves the values of v at these three nodes. And likewise, when we want the derivative here at L1 plus, we will use the one-sided derivative formula that involves these three nodes. Okay? And so, just to explain a little in a little more detail, then, at nodes, if we consider this to be node 1, this is node 2, node 3, this is node I minus 1, and then our interface is at node I, capital I here. So at node I, we will have our boundary condition, V1 equals A. At node 2, we have, let's go back up to our equation now. What do we have at node 2? Okay, I think I'll go right here. Now, node 2 is actually in a homogeneous region. See, let me make sure this is clear. Our problem that we're looking at here is that epsilon is constant and equal to epsilon 1 over here, and epsilon is constant and equal to epsilon 2 over here. So both of these individual regions are homogeneous. Now the overall region is inhomogeneous because epsilon 1 is not equal to epsilon 2, so there's a sudden change in epsilon here at this interface. But the subregions are both homogeneous. So in both of those regions, individually, we come back up here and we have this equation, d squared v dx squared equals 0. It's only at the interface that we have something different. So when we come back down here to the problem that I want you to code, okay, at node 1 we have the boundary condition v1 equals a. And then at node 2 and node 3 and all the other nodes up to I minus 1, we're just going to have the same kind of equation we had in our in our earlier projects. We have here, for instance, at node 2, we would have v3 plus v1 minus 2v2 over delta 1 squared. And then at node 3, we would have v4 plus v2 minus 2v3 over delta 1 squared. Delta 1 is the spacing in region 1, and delta 2, here it is, delta 1 is the spacing in region 1, and delta 2 is the spacing in region 2. And then finally all the way up to node I minus 1, we would have vi, the node to the right, the value just at the node to the right plus the value at the node to the left minus 2 times the value at that node. So vi plus vi minus 2 vi minus 1 over delta 1 squared equals 0. So I think all of these equations should make sense to you. And now let's jump down to and likewise what you have, I guess I haven't spelled it out here, but you'll do a similar kind of thing for all the nodes to the right of the interface. Like for instance here at the last node you'll have Vn is equal to B because our boundary condition there is B. But for nodes I plus 1 through n minus 1, at each one of these you'll just have the same kind of equation we had before. For instance, at I plus 1 you'd have Vi plus 2 plus Vi minus 2Vi plus 1 divided by delta 2 squared. So is equal to 0. So the equations for all these nodes would be very familiar. It's only at this node right here at the interface where we have something different. And there, our formula, keeping in mind that we're now using the one-sided derivative formulas, this is the formula you would get. Delta 1 over 2 delta 1 squared times Vi minus 2 plus 2 delta 1 over minus delta 1 squared Vi minus 1 plus 3 delta 1 over 2 delta 1 squared Vi times epsilon 1. This is all our one-sided derivative formula for dv dx just to the left of I1, and that's equal to this, where this is our derivative formula for the derivative just to the right of I1. And of course that one gets multiplied by epsilon 2. And you should definitely take a careful look at these formulas and make sure you understand where we're getting those formulas and exactly why you have negative signs where you do have negative signs. So be careful about that. Make sure you understand it, and if you have any questions, be sure to ask in the lab. And so now, as I say, I want you to code that up, and as usual you'll want an analytical solution to compare to. So let's look at that analytical solution real quickly. How would we solve this problem analytically? Well, since region 1 is homogeneous, we have d squared v dx squared is equal to 0 in region 1. And as we learned before in project 1, that means that the solution in region 1 must have the form c1x plus c2. Likewise, in region 2, it's also homogeneous, and so v must have that same kind of form in region 2 as well. So here we'll say c3x plus c4. So now the question is, okay, if v is equal to c1x plus c2 in region 1 and c3x plus c4 in region 2, then how do we find the four constants c1, c2, c3, and c4? Well, we need 4 conditions. And what are those 4 conditions? Well, one is that v is equal to a when x is equal to 0. That will help us to find, actually, that'll determine that C2 is equal to A. Another boundary condition is that V is equal to B when X is equal to L. So that will apply here to this expression, and that will help us to find C4 and C3. And then we need 2 more conditions, and the 2 conditions are what? Okay, we've outlined 2 of them. We said at X equals 0, we get C2 is equal to A, and then since X equals L2 is in region 2 and V of L2 equals B, we can say C3 times L sub 2 plus C4 is equal to B. And then now our 2 other conditions we have at the interface, epsilon 1 dv dx is equal to epsilon 2 dv dx to the right. So we have epsilon 1 C1, because C1, notice that C1 here, dv dx in region 1, if you take the derivative of the right hand side, dv dx in region 1 is C1 and dv dx in region 2 is C3. And so condition we have at the interface, remember this is our condition at the interface, epsilon 1 times dv dx just to the left of L1 is equal to epsilon 2 times dv dx just to the right of L1. So that becomes epsilon 1 times C1 is equal to epsilon 2 times C3. And then the final condition right here, where is that coming from? Well, V cannot take a sudden jump at the interface. Why not? Because E is equal to the negative of the derivative of V. And so that derivative, if V took a sudden jump, then you have essentially like a infinite derivative there, and therefore you'd have an infinite electric field. But we can't have an infinite electric field, and therefore V cannot take a sudden jump, and therefore C1x plus C2 evaluated just to the left of x equals L1 must be equal to C3x plus C4 evaluated at x just to the right of L1. And so that's where we get C1L1 plus C2 equals C3L1 plus C4. So you have, this is one equation, and then two equations, and three equations, four equations, and the four unknowns C1, C2, C3, and C4, and so you can solve for those. It says you have to solve for the four unknowns C1, C2, C3, and C4, and so that of course then would give you the analytical solution. So the next project will be to write a code for this problem, and once again you should, as usual, you should make L1, L2. N1 is the number of nodes in region 1, N2 is the number of nodes in region 2. A and B are your boundary conditions. Epsilon 1 and epsilon 2 are the values of the permittivity in the two regions. All of those, as usual, these should be things that you set in the first part of your program, and they should be easily variable. And you should write your code so that it will output a plot of your numerical solution of V and also the analytical solution for V on the same graph. And that's it. So good luck. And that concludes lecture 6. Help me. I can't find where to turn it off. I made a mention, I can't find it. Stop.